I'm going to talk about the possibility of formation of, here I have to make a remark. I say Earth-like planets. It's not precisely correct. It's far away. It's Earth-sized planets. So the possibility of formation of Earth-sized planets in the habitable zone of binary star systems. So we all know that there are many stars that are not single, and there are plenty of planets that have been discovered. But in terms of binary stars, we have 156 is about the number. And from those we call the orbits of planets of P type around 20. Just to quickly explain, so you have a binary star system, and you may have the orbit of the planet around one of the stars. That would be a S-type, like a satellite. And if you have a circumbinary planet, we call them P-type, like planets. So P and S for that. So we are talking about circumbinary planets. So the idea is the following. We from those 21 cases, we select those that we had, let's say, better data, more like complete full data that could be simulated. And so we reached this number of 6 systems. So here we have the mass of the first 2 columns, the second and third column. Here we have the mass of the stars, the semi-major axis and eccentricity of the stars, and then the mass of the planets, the position, orbital elements of the planet, the mass of the planet, and the last column is the habitable zone. It's an average approximation of that size. And so we are going to consider the 6 systems. And here, well, when we talk about habitable zone, I think we are going to have some more talks on that. It's quite complex. You may have a lot of issues on that. But if you're talking about a habitable zone around a binary system, it's a little bit even more complex, because it's not fixed like this green area I show here. It changes as the binary in the middle changes its position in the orbit, so it's a little bit more dynamic. But for what we want to see here, that's not the major point for a while. And so here I'm going just to show a few plots of the habitable zone for each one of the 6 systems. So in the middle we have the binary system, the orbits. In blue we have the orbit of the known planet. So we selected the binary systems that with known planets. And then we have the habitable zone. So this is Kepler 34, here it's 35. So the first one, it almost touched the habitable zone. The second one is inner. The planet is inner. And the other one is even inner, closer to the binary system. Then here we have a binary system that is a little bit more wider, and the highly eccentric planet orbit. Here, the habitable zone contains, the planet is somehow inside the habitable zone, and this other one, it's even more in the middle of the habitable zone, the known planet. So the idea is to question if we could form a planet with Earth-like size in the habitable zone of this system. So we have a binary star and this planet, and the issues about stability and the formation, aggregation of material to form that. So that's the main issue we are talking here. We are not discussing much more than that. So the simulations, we do not know much about the disks. Even in the solar system, we have just a talk by André. So we have a lot of details about how to distribute the mass and the composition of the disk. Here we followed what's somehow a little bit standard, used for solar system terrestrial planets formation. But considering the binary stars, planet, and the disk, so the disk follows this kind of stuff. We have a total mass of around 33 Earth mass. Half are embryos and half are planetesimals. Planetesimals are much smaller and they have some importance in producing the reduction of the eccentricity of the system. So there's a distribution of mass in that. So that's not a real issue here, but I'm just showing that we followed one pattern, but then we have to do that, making some changes to see how that changed the results. So, and we distribute that mass in the habitable zone. We considered near circular orbits and near coplanar too. So here we have just the distribution of mass. Here is the mass distributed by some major axis. And the colors correspond to the real value of the mass. So I say preliminary results because we are talking about some stochastic dynamical system. So you have to make several simulations and have an interpretation of that following the statistical results you get. So what I'm going to show here are typical cases that reproduce more or less on average what we get from our simulations. So for each one, we did at least 10 simulations with small changes on that. So here we have for the first system. In the corner we have a shorter plot of that habitable zone and the orbit of the planet. And here, so here we have snapshots for different times. So here when we start, here's the semi-major axis and eccentricity. In the light blue is the habitable zone. And this line corresponds to the line of crossing the orbit of the planet. So if the particle will cross this line, it will be crossing the orbit of the planet. So it's a good guide for the dynamics, to understand the dynamics of the system. And so as it evolves, so here how we start. As it evolves, here the planets grow, and we get here the largest one, this green color that corresponds to about half the Earth mass. So, and the time of integration, following what we have more or less for the inner solar system, the terrestrial planets, is a few 100 million years. So here is for 200 million years, and we got, the largest body we got is half the size of the Earth, or smaller than that, and it's outside the habitable zone. That's more or less what happens on average for this system. So this is one case that it's quite difficult to get an Earth-sized planet inside the habitable zone, despite seeing that the planet that already exists is inside the inner to the habitable zone, so it's not on that. And if we pay attention to the picture in the corner, so the next one we see that the blue curve goes inner, and so that allows us to have a more stable region inside the habitable zone. And then we managed to, in half of the time of the previous simulation, just 100 million years or less than that, we get more than one planet inside and of the order of the size of the Earth in terms of mass. And the next one, also again in the corner, if you pay attention, it's you have an even smaller one. But here we can get a planet inside the habitable zone, but the length of time is much longer. And that is because we need a planet to shake the particles that are inside the habitable zone to grow. So that affects the length of time you need for the simulation to get the body. So here it's more stable, but the body is farther from as a disturber, and its mass is also smaller than comparison to the previous one. And this next one, we have a body that is just near the border. We managed to get a body near the border of the habitable zone, the outer border. And so we have cases that allow us to get or not, depending, so the main parameters here, the mass of the stars, the separation of them, and the known planets. And then the next one, it's a case where we almost do not manage to get the bodies formed inside the habitable zone. So the planet that already exists disturbs it so much that do not allow them to grow much. So once they get a little bit larger, they are expelled from the region. And so the last one, let's make separation here to make some comments. It is in, let's say, somehow in the middle of the habitable zone, the already known planet. It has about more than 1 Jupiter mass. And so the distribution of material on that, we may have inner and the outer region. And so also in the region where the coorbital to the body. So here we have a small simulation we did just to study the stability. So here we have a major axis and eccentricity distribution of bodies. These two black lines give the conditions that where the particles cross the orbit of the planet, and we distributed particles here. So as they evolve, we have here further stable, here in the inner border of the habitable zone stable a little bit, here it's not, here's the same. And one interesting thing is that we have a stable here that's coorbital to the body. So we have inner and outer and coorbital regions. So we have 3 possibilities of stable regions where we might have the formation of a planet in there. Here we show the inner parts. So for a simulation, the inner part, we do manage to form a body with a good size, but it's outside of the habitable zone. The outer part is similar to this one, so I didn't put it here. And then we have the coorbital part. The coorbital, they are quite well known in the 3-body problem. So if you have a central mass, a secondary mass, you may have in this rotating system equilibrium points, and in special these 2 Lagrangian points, L4 and L5, might be stable. For this case, they are stable for their mass ratios. But here we have something a little bit different. We have a binary here. And this planet is somehow a little bit inclined. So we try to distribute particles in the coorbital region. So just going back, around those points, L4, L5, you may get stable orbs that behave like a shape like a tadpole orb. That is well known for the Trojan asteroids with Jupiter. And so we tried here several possibilities, changing mass, changing parameters. And by the end of the day, these regions are stable for massless particles or small particles, individuals. As they start to grow, one push the other, and very easily they are removed from the coorbital region, and they do not manage to grow anymore. So at most we get bodies of the size of the moon, are the largest we get in this region. So despite being stable, and well, there is no possibility of forming larger bodies like the Earth-sized bodies in this region. So the growth is somehow unstable. The region is stable for particles individuals, but as they grow, the region becomes unstable. Thank you.